Good morning, last day of the workshop. I hope everybody's excited. We're going to kick off with some next steps in astrometry. And first up, we have Aki Roberge from NASA, who's going to be telling us about detecting Earth. Very great topic. Take it away, Aki.
Okay, great. Thanks, Jackie. How's that? Mic okay? All right. Great. So I'm Aki Roberge from NASA's Goddard Space Flight Center. And so I'm going to talk to you today about the path towards finding potentially habitable exoplanets and characterizing them and actually searching them for signs of life. And so this really ambitious goal, it's within our reach in the coming decades, but it's extremely challenging. And so as you'll see, we really do need to bring to bear all the techniques that we have to study exoplanetary systems. Okay, oh, I see. Where? Down arrow? Yeah, okay. Okay, so I'm going to start by setting the stage a bit. So there were several community reports going back to well before the last decade that expressed a general consensus on the search for life in the universe. And first, that success in this search would be one of the major scientific achievements of the century. And then second, that there are two paths towards characterizing potentially habitable exoplanets. And hopefully by the end of this talk, you'll see why there are two. So for the exoplanets that are most like the only known inhabited planet, those around sun-like stars, we'll need direct spectroscopy with a space-based telescope. Then for the potentially habitable planets around the low-mass M-dwarf stars, the path goes through direct spectroscopy with the future ground-based extremely large telescopes. Okay, so just to make sure we're all on the same page about what direct spectroscopy means, here's a simulated image of a direct image of the inner solar system. And you saw this image earlier this week, and there was a question about what these colors mean. So I'll explain it at the end because it'll make more sense after you see some of the other stuff I have to say. So at the center of this image would have been the blazingly bright host star just blasting the whole detector, but it has been suppressed with a coronagraph to produce this high contrast image that reveals the faint planets in orbit. So nothing can be seen within the central suppression region, which is called the inner working angle. And I'm going to return to that later. Okay, so light coming directly from the planet with little or no starlight mixed in will be dispersed into a spectrum that will hopefully reveal the signs of habitability and atmospheric biosignatures. So the y-axis there shows the planet to star flux ratio, which for the Earth around the sun is about 10 to the minus 10. So this observation requires a really extreme level of starlight suppression, or in other words, extremely high contrast. Okay, so I'm going to take a few minutes to summarize the logic from all of those reports that led to the two paths. So you can get it in 2 slides instead of like 5 documents. Okay, so starting with the potentially habitable planets around the sun-like stars, the planets are small and they have high mean molecular weight atmospheres. So they're very short, they have small scale heights. And the stars are relatively large. So this results in unfeasibly small atmospheric signals in transit spectra. And therefore, we need a direct spectrum. So then the 10 to the 10 contrast that you need for direct spectroscopy of Earth-like planets around sun-like stars, that appears too difficult for coronagraphs on the future ELTs, even with help from extreme adaptive optics and other techniques like high dispersion. So higher contrast will be possible with a space-based telescope because there's no, we're not looking through Earth's atmosphere. And that's how you recover path 1. Okay, so now we turn to the low mass stars. So again, we have a small planet with a small atmosphere, but now the star is small too. So the atmospheric signals in transit spectra, they're still small, but they're larger than they were. However, a transit spectrum is preferentially sensitive to the upper atmosphere of the planet. And some important molecules are concentrated in Earth's lower atmosphere. So in particular, water vapor, which is key for diagnosing habitability, is only present in the lowest layer of Earth's atmosphere, in the troposphere. So again, we need direct spectroscopy, which can reach all the way to the planet's solid surface as long as the clouds aren't too dense. Then the planet to star flux ratio for an Earth-like planet around a low mass star is larger than it is for a sun-like star. So therefore, the contrast requirements for direct spectroscopy are much less extreme. So we should try to obtain these observations with the future ELTs. And I will, whoops, I forgot to advance. Whoops, sorry, there we go. So I will revisit the explanations for these two paths in a bit more detail later. Okay, so down arrow. Okay, so now I'm going to talk about how we pursue path one. Okay, so NASA's great observatories, they spanned a huge swath of the electromagnetic spectrum, and they really transformed the whole field of astronomy. And it's hard to imagine our field without these facilities, but two of them are no more, and Hubble and Chandra are starting to show their age. So from 2016 to 2019, NASA did 4 studies of large space observatory concepts, and this was in preparation for what's called the Astro 2020 Decadal Survey. So for those who don't know what that is, every 10 years, the National Academy of Sciences assembles a large team, actually it's multiple teams of eminent scientists and technologists to consider a huge amount of input from the whole astronomy community, and not only in the US. The team then sets priorities for the future of astrophysics, both in space and on the ground. And they make recommendations to guide NASA, NSF, and the Department of Energy about activities of all size scales, all the way from like research and analysis grants to flagship space missions. So Hubble, Chandra, Spitzer, JWST, and Roman were all endorsed by previous decadal surveys. Anyway, so returning to more now, the mission concepts that were studied in preparation for Astro 2020 were the Habitable Exoplanet Observatory, HABEX, the Large UV Optical Infrared Surveyor, LUVOIR, the LYNX X-ray Observatory, and the Origin Space Telescope. That one was a far infrared mission. And I was the NASA study scientist for LUVOIR. Okay, so last November, we found out what the Decadal Survey thought, and they said that the time has come for NASA to work towards a new fleet of multi-wavelength great observatories, more powerful than the first generation. So Astro 2020 also recommended that the first of the new great observatories be a large UV optical infrared space telescope with a roughly 6-meter inscribed diameter. If there's time later, I can explain what that keyword inscribed means is about. So this mission should be a super Hubble that can perform a huge range of revolutionary astrophysics. But unlike Hubble, this telescope would actually be designed to find truly Earth-like planets around sun-like stars and see if they harbor life. So this recommended telescope is a blending of 2 of those pre-decadal mission concepts, LUVOIR and HABEX. And we don't have a name for this mission yet. Some people are calling it IRUV, but that's awful. So for the time being, I'm calling it LUVEX until I'm told otherwise. And that's not great, but it's better than IRUV. So anyway, Astro 2020 said that we should start maturing this mission concept as soon as possible. And all going well, it could launch in the early 2040s, which is pretty typical for a flagship space mission. Okay, so this plot shows the estimated yields of different kinds of exoplanets discovered with 2 variants of LUVOIR during the Habitable Planet Survey. So obviously we don't have a design yet for LUVEX. So what I have to show you is the results from the previous work, the previous studies from before the decadal. So LUVOIR B had a large 8-meter diameter primary mirror measured from the segment tips. LUVOIR A had a really large 15-meter diameter. So the discovered planets range from rocky planets, both larger and smaller than Earth, to gas-rich sub-Neptunes, to Neptune and Jupiter-sized giant planets. The host stars are mostly solar-type FGK stars with a few handfuls of low-mass M-dwarfs and a very few, like 3 or 4 high-mass A stars. So LUVOIR A was expected to find and study about 54 habitable planet candidates, while LUVOIR B expected to study about 28. And here are the expected yields for HABEX. So there's a lot more detail about all of, whoops, okay, down arrow, geez. Okay, so, and those are the expected yields for HABEX. And there's a lot more information about how all of these things were calculated, what assumptions went in. You can find all of that in the LUVOIR and HABEX final reports. Okay, so the key goal for LUVEX set by the Decadal Survey is to search for biosignatures from about 25 potentially habitable exoplanets. And this is a robust sample size that will allow us to measure the frequency of Earth-like planets and global biospheres in the solar neighborhood. Okay, but once the habitable planets are found with LUVEX, we're not just interested in like fuzzy dots. We need spectroscopy. But it's critical to realize that the Earth has had a global biosphere for most of its existence, but it hasn't always looked like the modern Earth. So the left side of this figure shows the history of Earth's atmosphere. So the y-axis is in billions of years, and the x-axis shows the concentration of major gases. So, and it illustrates how the bulk atmospheric composition of our planet has changed dramatically over billions of years. Modern Earth spectrum there, that's our usual starting point for thinking about Earth-like planets, but that's representative of only about 13% of the planet's total inhabited history. But at this stage, there is a high level of oxygen in our atmosphere produced by photosynthetic life. And so a key biosignature we would look for is molecular oxygen, O2. Okay, but now we're going to step back in time to the Proterozoic. And this actually lasted for about half the history of life on Earth. And during this time, Earth's atmospheric oxygen levels were much lower than today. And they were likely too low to allow molecular oxygen, to allow O2 itself to be observable. So at these low oxygen levels, you need to observe ozone to show the presence of oxygen in the atmosphere. And fortunately, there is a strong O3 absorption band in the near UV there. So without the ability to measure ozone, one could easily identify the Proterozoic Earth as a habitable but uninhabited planet. That would be a false negative in the search for life. Okay, and then lastly, we'll consider the Archean Earth. That's about 40% of Earth's history. And at that time, our atmosphere contained no oxygen at all. The biosphere was dominated by methanogens, and methane is a critical atmospheric biosignature. Okay, so the broad wavelength coverage of the LUVEX high contrast spectroscopy was chosen specifically to allow identification of Earth's biosignatures throughout its inhabited history, well as we know them. However, I do want to emphasize that no one molecule or even pair of molecules is a biosignature in every context, in every stellar and planetary context. So the key to identification of biosignatures is to quantitatively understand the sources and the sinks of the atmospheric constituents, and then look for the high source rates that can't be explained solely with physics and chemistry. So that's really how we're going to do this. I know in the past, people have talked a lot about disequilibrium chemistry or biosignature pairs and stuff like that. And that's just a subset of, that isn't really how you're going to search for, you need to search for biosignatures. Because there's disequilibrium chemistry all over the place in solar system planets, and it's not caused by life in most cases. Okay, so LUVEX was envisioned as providing high contrast spectroscopy at near UV to near infrared wavelengths, using a chronograph and possibly also a star shade to suppress the host stars. The European Life mission concept uses another approach to get the direct spectroscopy. So instead of looking at reflected light, it would observe mid-infrared thermal emission from potentially habitable exoplanets. So, and what they do that by using multiple free-flying telescopes to combine light destructively and to suppress the central stars, but not the planets orbiting them. And so this is called nulling interferometry. So LIFE draws upon two older mission concepts. So ESA's Darwin mission and NASA's Terrestrial Planet Finder I mission. And both of those were studied in the early to mid 2000s. Okay, so the design for LIFE is not set as far as I can tell, and therefore I'm not exactly sure what it could do. But I will say its prime science objective is to search for biosignatures from a few dozen potentially habitable exoplanets. And the planets would be orbiting early M to late F stars. However, LIFE would be more sensitive to habitable zone planets around low mass stars. So there's actually only moderate overlap with the LUVEX target list. So as far as I can tell, the current status for the LIFE mission is that early concept study activities have started in Europe, and the team is seeking support for further work. Okay, so now I'm going to talk about how we pursue path 2, and I'll revisit again why there are the two paths. Okay, so I'm absolutely thrilled about JWST. The first science images are amazing, and I can't even keep up with the high Z galaxies that keep pouring in and in and in. On my Twitter feed, oh, new one, Twitter, no, oh, no, another one. So, but you know, for us, the better news is that 25% of the first year of JWST operations, that's going to be spent observing exoplanets. And a fair chunk of that time will be spent on the very special TRAPPIST-1 M-dwarf system. And that's because TRAPPIST-1 represents JWST's best opportunity to probe the atmospheres of potentially habitable terrestrial planets. So what we know about those planets right now. So the innermost 6 do not have light, puffy, hydrogen, helium dominated atmospheres. But we can't yet tell whether the planets have high mean molecular weight atmospheres like Venus or Earth, or whether they are bare rocks like Mercury and, sorry, Mars, which is, you know, Mars at interstellar distance is a bare rock. Okay, so in the first year of JWST science operations, that's cycle 1 for those who don't know our jargon, there will be programs to search for atmospheres on several of the TRAPPIST-1 planets, those right there. And I'm sure that the 2 that are most, that doesn't include the 2 that are most solidly in the habitable zone, E and F, but I'm sure those will be extensively studied once we know more about, well, I'm sure they'll be studied anyway, once we know more about JWST's exact performance. And so this plot from a group at the Virtual Planet Laboratory at the University of Washington, it shows how hard it will be to detect an atmosphere for each of the TRAPPIST-1 planets. So the numbers say how many transits you would need with JWST to rule out a featureless flat spectrum for different self-consistent feasible atmospheres. So for most of the planets, the numbers are what I would call quite reasonable. But sadly, the likely best habitable planet candidate, TRAPPIST-1e, of course, it's, wouldn't you know, it's the hardest. Still, in my opinion, even 31 transits would absolutely be worth it, but that's just my opinion. Okay, but then can we go further and use JWST to find out what the atmosphere of a potentially habitable exoplanet is actually like by detecting specific molecules? So this plot shows simulated JWST spectra of TRAPPIST-1e created using Natasha Batalha's Pendexo code. And the orange and red models are CO2 dominated atmospheres with and without Venus-like clouds. And the cloud-free spectrum takes 30 transits, while the cloudy spectrum takes 120. So then the teal and blue models are water-covered aquaplanets, both with and without clouds again. The cloud-free spectrum takes 50 transits, while the cloudy spectrum takes 90. Okay, so you can see the presence of clouds and hazes, which are ubiquitous on solar system planets that have atmospheres. Even Pluto has hazes. Makes it extremely hard to detect molecules of any kind in the atmosphere. And furthermore, if you look closely at the aquaplanet spectra, you'll see, actually, maybe, I'm gonna try it here, see if I can do this. Where's the mouse? There it is. You'll see that the most prominent features actually come from CO2 right here. And that the water vapor features over here are extremely small in both cases. And this is because the water vapor is concentrated at lower atmosphere, at lower altitudes in the atmosphere, which, as I mentioned at the beginning. And so I had forgotten to click. There's the thing about clouds and hazes, sorry. Okay, so this work is broadly consistent with other JWST simulation efforts. And so it looks like it would take a major investment of JWST time to detect any atmospheric molecules, even for the best potentially habitable planet candidates. And detecting water vapor in a potentially habitable atmosphere, that looks to be out of reach for JWST. And I'm not, yeah, so I guess. Okay, so now we'll see what the ground can do for us. So there are 3 possible future extremely large telescopes on the ground. There's the European-led ELT, the US-led 30-meter telescope, and the US-led Giant Magellan telescope. And first light for the ELT is planned for 2027. The other 2 are less certain. So in addition to the Astro 2020 recommendation to proceed with LUVEX, the Decadal Survey also recommended significant investment in TMT and GMT. Okay, so now I'm going to revisit the 2 paths again and try to explain in more detail why we can try a ground-based path for potentially habitable planets around M-dwarfs. Okay, so this cartoon shows the habitable zone around sun-like and low-mass stars. In the sunlight case, an Earth-like planet has an extremely low planet-to-star flux ratio, that 10 to the 10 contrast that I mentioned earlier. So that's bad for direct observations. But the habitable zone is further from the star. That's good for direct observations. In the low-mass case, it's flipped. The planet-to-star flux ratio is higher than it was before. It's still small, but it's higher than it was before, but the habitable zone is smaller and closer into the star. Okay, so now why do those facts matter? Coronagraphs, they suppress the central star so that faint planets can be observed. That suppression region is called the inner working angle, and planets have to be outside of it to be seen. The inner working angle is proportional to the wavelength of observation over the diameter of the telescope. So larger telescopes have smaller inner working angles, and planets can be seen closer into the star. Okay, but that's not all. Extreme starlight suppression requires a high quality, stable wavefront hitting the coronagraph. So without Earth's atmosphere in the way, you naturally get a more stable wavefront. And that means higher contrast is possible from space. And you can observe planets with lower planet-to-star flux ratios. So the variability of Earth's atmosphere limits the contrast achievable from the ground. And even when using future extreme adaptive optics and other techniques, that 10 to the 10 contrast you need for Earth's around suns, that appears to be out of reach for the ELTs. So to put it all together, the direct observations of habitable planet candidates around sun-like stars, they need the extremely high contrast possible from space. And the habitable zones are larger, allowing the planets to be outside of the inner working angle, even with a relatively modest 6-meter telescope like LUVEX. Okay, but then on the other hand, direct observations of habitable planet candidates around the low-mass stars, they need the extremely small inner working angles made possible by those enormous ground-based telescopes. And fortunately, these planets should be observable even with the worst contrast possible from the ground. So thus the complementary strengths and weaknesses of both space and ground-based observations here were sort of matched to these two different stellar environments. Okay, but it's still not going to be easy. Quality ELT spectra of potentially habitable exoplanets, I believe will likely need several things: high performance coronagraph, new extreme adaptive optic systems, and possibly also new techniques like combining high contrast with high dispersion, high spectral resolution. And it looks to me like there is one of the first generation instruments for the European ELT, the METIS instrument, combines all three of these characteristics. However, I don't see any similar first generation instruments planned for TMT or GMT. Okay, but let's see, where am I? So the burning question though is how many habitable planets can actually be studied with the future ELTs? And to be honest, I have to say I don't know right now. And I expect that the answer to this question awaits additional instrument design work, better understanding of instrument performance, better understanding of future AO performance, and also further observational simulations. Okay, so that was the direct part of my talk. Now I'm going to turn to the critical roles of indirect observations that have in both of these paths of the search for life. Okay, so first of all, and this is not exactly breaking news, planets are complicated. So this figure shows the things that the solar system and Earth and exoplanet theorists think matter for truly understanding a planet and how it came to be. So I'm not obviously gonna go through all that, but there are stellar properties, there are features of the planetary system, and then there are a whole host of planet-specific properties. And furthermore, we've also now recognized that life itself is a planetary process that co-evolves with the environment. So I really cannot emphasize enough that exoplanet studies in general and habitability and life in particular require input from many fields, both within and outside astrophysics. And direct spectra are central to our efforts to search for life, but figuring out if we've actually found some will need lots of other data as well. So given all of that, having a thoughtful observing strategy is critical. And this is the search for life strategy that was developed by the LUVOIR team. Its guiding principles can be described as completeness and efficiency. And this strategy drew upon a very active last decade in exoplanet and astrobiology research to identify key questions that need to be answered for a definitive result. And those are down the left of the pyramid there. Okay, so then we identified the measurements needed to answer those questions. And while we were doing that, we considered what information can be obtained with other current or planned facilities. And the remaining needs drove LUVOIR's capabilities. So again, this strategy is explained in far more detail in the final report, but science doesn't stand still, and all of this should be reconsidered. Okay, so I'm just gonna work through a few rows of the strategy pyramid that involve indirect observations. Okay, so first of all, we obviously need the planet's orbit to know if it's in the habitable zone at all and to understand the impact of the star. And that can be readily obtained by directly observing the planet over multiple epochs. But then once we have the orbit and we get the stellar spectrum, we can calculate the key input to the planet's heat balance. And the stellar ultraviolet is especially important since those wavelengths drive the planet's atmospheric photochemistry. And quantitative understanding of that process is absolutely critical for determining those source and sink rates of molecules that I mentioned earlier and identifying biosignatures. And then the stellar wind is a key factor in determining whether there is significant atmospheric mass loss from the planet. Okay, next we need the planet mass. So this is important for modeling the surface gravity and the atmospheric structure. So we don't need super precise masses, but we do need them. The current radial velocity measurements from the ground can provide minimum masses for higher mass planets. If you combine that with inclinations from direct imaging, you'll get the true masses. So then I expect that the higher signal to noise provided by the future ELTs will allow mass measurements for smaller planets and maybe even more importantly, planets around noisier stars. But the key question is whether we can use future RV on the ground to get down to Earth mass planets around sun-like stars. And we'll want to be able to do this for all the LUVEX targets, whether the host stars are quiet or not. We don't get to be choosy about that. Okay, so if we can't, then hopefully astrometry will come to the rescue. So as mentioned this week, this technique is relatively unaffected by stellar activity. So as you've heard, Gaia will provide masses for an enormous number of large exoplanets. The upcoming Roman Space Telescope can also do astrometry, and Scott Gowdy will talk about that later today. And then there's the possibility of new dedicated astrometry missions, and there are a few talks about that coming up next. And then finally, basically, in the last resort, the LUVOIR team incorporated a high precision astrometry mode into the onboard wide field imaging camera, which is primarily aimed at astrophysics studies, but has this important application as well. But a lot of work will have to be done in the coming years to determine what's the best path here. Yeah. Okay, so finally, then there's my old friend and nemesis, exozodiacal dust. So this is dust coming from the destruction of asteroids and comets. It's the debris that gives debris disks their name. And this figure shows our best knowledge of the structure of interplanetary dust in the solar system. So Exozodi is likely to be the largest source of astrophysical noise in direct observations of potentially habitable exoplanets. It drives up the exposure times, and it can hide the planets altogether if it's too bright in the wrong places. So in my research, back when I did some on debris disks, Exozodi is my signal. In my LUVEX life, Exozodi is my noise. Okay, but fortunately, we've known for a long time that Exozodi was a worry. So NASA funded construction of the Large Binocular Telescope Interferometer specifically to address this. And the LBTI instrument uses nulling interferometry from the ground on the LBT to measure mid-infrared thermal emission from Exozodi in the habitable zones of nearby sun-like stars. So the key survey is complete, and fortunately, it looks like typical dust levels are not too high for LUVEX. Okay, so however, there is more to do on Exozodi with the chronograph on the Roman Space Telescope. So that will be able to image Exozodi in optical scattered light, and that would provide a check on some of the model dependencies that were involved in interpreting the LBTI data. Okay, and so I promised I would say something about helpful near-term next steps. So there are really a great many, but here are a few that might be of particular relevance to this crowd. So first of all, we did a lot of science simulations for LUVOIR and HabEx. Those will need to be redone for LUVEX, and they should also be improved and expanded. And one that really needs improvement is the calculation of LUVEX onboard astrometry capability. And if anyone is in, like, for example, we assumed single planet systems, you know, we made a lot of, to be frank, I'm not sure we completely knew what we were doing, but it sounds at least like, thankfully, it sounds like we got the hardware right anyway, but I won't vouch for anything about the exposure times required to do what we said that it could do. But anyway, suffice it to say, if anyone is interested, come talk to me. Okay, so next, we need to make sure that the prime targets for LUVEX are getting sustained RV monitoring. And we want to know about all the planets in the system, not just the Earth mass ones. And anyone who's interested in that, making sure that gets coordinated, don't talk to me, go talk to Eric Mamachek. Okay, and then finally, we should collect far UV spectra of all the exoplanet host stars that might be targeted with JWST before the end of Hubble. So some of this is happening, but I think a bigger upfront effort is warranted since we don't know how much overlap there will be between the HST and JWST lifetimes. And without HST, you will not be getting quality ultraviolet spectra of these stars. Okay, right, so hopefully I've shown you there is a really exciting future in front of us. There are complementary paths in the search for life in a wide range of stellar environments, and we're actually going to go down both of them. But it's going to be complicated, and we really will need all hands on deck quite soon. So you might think, what's the rush? The ELTs are being built, and LUVEX isn't going to launch for about 20 years. But when it comes to instrument and mission development, input from the scientist is most necessary, most critical at the beginning of development and at the end. So now is the time for us to figure out what these future facilities are actually going to do. So anyway, I hope you'll be interested in contributing to that effort. Okay, so that's the talk. Should we do questions or whatever? That's great, clap, whatever. Okay. Okay, but I did promise to hop back to that chronograph image and explain what those colors were about. Do I have to? How do I do that? How do I do that over here without messing it up completely? Can I hop back like a bunch of slides somehow? No. Just oh, it's gonna take forever if I do it that way.
Oh, you want to escape? While Aki's doing that, why don't we take any questions that you guys have? You can use the mics, or we can go to the Slack comments.
So we have a few questions from Slack. The first one is asking which molecules can you expect to be the best candidate for high mean molecular weight atmospheres in TRAPPIST system?
High mean, habitable or inhabitable, I wonder. Well, for habitable anyway, I'm going to go TRAPPIST 1E, why not? But I don't know. I really don't. E, F, I think it's kind of a E or F. It's kind of a crapshoot for having an atmosphere for a potentially habitable planet. That's just a wild guess. There's not much behind that.
Just to build on that too, because Aki, you said you were happy with 31 orbits.
I am.
31. I mean, that's a lot of JWST time. Another comment on that, maybe? I don't know. Like, what's the biggest pitch you think? Because you're that confident that we would be able to say something so powerful that the community.
Well, I think finding out for sure whether habitable zone planets or rocky planets in or near the habitable zone of M-dwarf stars, whether they can have atmospheres at all, is absolutely critical. We need to figure this out because I mean, there have been many papers on many theoretical reasons why those planets shouldn't have atmospheres. There's the enhanced stellar activity, the high levels of wind, the flaring. They have higher levels of coronal mass ejections. They also have a very long pre-main sequence phase, where during which the possibly habitable zones of the planets would really get baked out. On the other hand, there's also a whole other pile of papers that say that's all not true. There's no reason you can't have atmospheres on habitable planets or on dwarf stars, because you could get outgassing, a second atmosphere produced by outgassing from the interior of the planet, which actually happened on Earth, so it's not crazy. And we're not going to solve this with arguments between the theorists. We're going to solve this by actually observing them. And the TRAPPIST ones are the best ones to actually say for sure. So just detecting whether it has an atmosphere at all would be huge.
All right, that's fair. Let's go to the questions here.
This is all really exciting stuff. Thank you. And I hope what I'm about to say comes off as a question. Is it concerning, like for future direct spectroscopy with large ELTs, is it concerning trying to do, would we get enough light from a planet to do spectroscopy around a low mass star?
But I believe so. But as I said, I couldn't find a lot of really specific quantitative information about exactly how many planets will be studied for how long, and this is what kind of data we'll get with the ELTs. So I didn't find a lot of detailed simulations. That doesn't mean that they don't exist. It just means, you know, they're not public or whatever. But judging from what I've read in like papers and stuff, I think it's possible. I mean, these are huge telescopes.
True.
So I do think it's possible. Not for perhaps a huge number, but, you know, some. I don't know, but some TBD, some. So.
Cool, thank you. Sorry for struggling to ask a question.
Yeah, that's fine.
Yeah, great talk. So you showed LIFE, the interferometry mission.
Mm-hmm.
And I know pretty much the entire community was burned in the mid-2000s with the collapse of Darwin and TPFI. Is there any reason that the US is also not starting to probe the space interferometry front like the Europeans are?
Well, you are correct that you know, TPFI and Darwin kind of had an ignominious end of life there. In fact, a total side note, I met my husband at the very last TPFI Darwin Science Conference, and our kid is now 11. So, back before, so all of this whole path stuff didn't start even with the decadal, the Astro 2020, or even those studies. Before that, there were some other studies. For example, there was something in 2013, there was the Visionary Astrophysics Roadmap. And for that, so we did consider that, like what's the better way to go, coronagraphy or interferometry. And of course, you know, back in the day, NASA was going to take both paths, and they ended up not doing either of them. So we basically went all through it and judged that the coronagraphy path, while difficult, was less difficult, less challenging than less technologically challenging than interferometer. And also too, it did in fact, we do in fact want these wavelengths. The near UV to near infrared wavelengths are actually quite key. And I think I recall Sarah Seeger saying once, if she had to pick only one bandpass to look at planets in, it was the near infrared. So, because there's a high density of molecular features there of a wide range of species. So it was sort of a view that coronagraphy first. That judgment was then also reconsidered at the NASA the ExoPAG, Exoplanet Program Analysis Group meetings. And the consensus there too is, yeah, that sounds like the right way to go.
Cool.
So
We'll take another one from the mic here.
Hi. When you were showing the demographics of the detections of the different types of planets with the different missions, obviously there's like some type of demographics built into that, like an A to Earth.
yes.
I wonder if you could talk a little bit about that, and then maybe what type of like future observations would help build that out.
Yeah, okay. So both Habex and Louvois, what we did try to do is we tried to use all the same input assumptions and methodologies so that we could do apples, so that everybody could get apples to apples comparisons. So we both assumed eta sub Earth of 0.24, which was the value from the this Exopag science analysis group did this sort of meta-analysis of all the literature and like checked, looked at some of the statistical methods and kind of came to like a consensus number. The error bars on that are large. So the figure that I showed, that's the pretty one for public consumption. It doesn't have error bars, but the guy who did all those calculations for both Louvois and Habex, it's Chris Stark from Goddard, or he was at Space Telescope at the time. He's super conservative and pretty anal. So his plots have error bars. So if you go into the Louvois final report, if you look into chapter 3, you can see the error bars. And most of that error is because of eta sub Earth, uncertainty in eta sub Earth. And I believe that, Chris ran it down to eta sub Earth value, I think 10% as his lower bound. Now, as we heard earlier, maybe, that might not be the lower bound. So we should look at that again. The easiest way to increase the yields there are a few ways actually to get the yields up if eta sub Earth is lower. For one thing, we threw out a lot of binaries because, like for example, like how do you suppress two stars? With a normal coronagraph, you don't. However, if the binaries are very close and they can both fit under the mask, that's probably okay. And if they're very wide, that's probably, you can suppress one of them. And that's probably okay too, as long as the stray light from the secondary is not too bright. But in order to know if the stray light from the secondary is not too bright, we don't just need to know it's a binary. We need the orbit and the delta magnitude between the two stars. So I've been actually harassing Todd Henry for the last 2 or 3 times I've seen him about people getting going on a really good binary survey for the potential LUVEX target stars. And like I said, not just like, hey, there's a binary. I need orbit and delta mag. So that's one thing. So if we could bring back a lot of those binaries, that would increase our yields even with eta sub Earth being rather low. So that I think is a good thing for this. I should have put that on the slide actually, because that's a really good thing for this group to work on actually. So.
Okay, any last questions?
We have,
Do I have a minute to promise to explain what these colors are? Can I do that?
Yes, why don't you do that? We've got a minute left here.
Okay, so things about coronography. Okay, so yeah. All right, so these are meant to be real colors, the real colors in reflected light of the planets. Earth is blue, like we expected. Oh, why does Venus look green? Okay, that's because of that whole thing about the inner working angle that I mentioned. It's proportional to lambda over d. So the inner working angle is larger in the red. So more of the red light from Venus is getting blocked, and you end up with this funny green color for the planet. Okay, similarly, all of these colors around the outer edge, chronographs also have outer working angles that are also proportional to lambda over d. So Rosé Joanola Paramon, who made this simulation, I actually like what she did. She left it in. Usually people mask out. They'd stop the image right about here, but she left them in, and I rather like it because you can see that the red light, the red light is further out than the yellow, than the green, than the blue, because the outer working angle is also moving outwards with wavelength. And that's what those colors about.
Nice. Okay, I think we're going to have to actually stop there because we're at 9:15. Yep. So let's thank Aki one more time in the room. Thanks, Aki.